This is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, we are going to discuss about the problems related to the common drain fit amplifier circuits. So, in this common drain amplifier, we are going to calculate the input impedance of the amplifier circuit and the voltage gain as well as output impedance of the given common drain amplifier circuits. So in order to calculate these parameters, we require the formulas for common drain amplifier. The current gain formula here it is the ratio of output current to the input current. In the ideal case, we will get it as infinity, but in the practical case, we will get it as large value. And in the voltage gain, that is also a ratio of output voltage to the input voltage. That is minus GM/RD by 1 plus GM into RS, where GM is the transconductance and RD is the drain resistance and RS is the source resistance. And next, to calculate the input impedance, that is the ratio of input voltage to input current, and ideally we will get it as infinite. And next, to calculate the output impedance, we will take output voltage to the output current ratio, and that is almost equal to the drain resistance or output resistance here. So these all are the normal expressions. Suppose if we go with the approximate expressions, so these all are, we have seen now, the exact analysis expressions. Exact analysis expressions, and the same thing if we go with the approximate expressions, we will get these particular formulas. Next, before going to solve the problems, in the case of CD amplifier, we will utilize the different biasing techniques in order to operate it as a proper operating point, and in order to operate it as the stabilized device to provide the proper amplification. So here it is utilizing the fixed bias or else self bias or voltage divider biasing. So any fit amplifier, that may be the common drain or common source or common gate amplifiers, can be utilize either fixed, self or voltage divider biasing techniques in order to provide the proper biasing for the amplifier circuit to get the proper amplification signal across the output here. So in the case of fixed bias circuit, we will utilize the fixed resistance between the gate and drain to provide the proper biasing here. We'll utilize the fixed resistance here, the fixed resistance value between the drain and gate terminals. And in the self bias, again between the drain and source terminals, we will add the resistance. So if you add the resistance, there is a variation in the bias voltage. So in this particular fixed bias condition, the stability factor, we will get it as very high. So the stability factor should be low to get the stabilized operation or to get the proper amplification across the amplifier. But in the case of fixed bias, the stability factor value is very high, so that we are not achieving the proper bias. So that's why we are moving for the self bias. In this case, compared to the fixed bias, the stability factor value will be decreases, so that the biasing level will be somewhat set in the case of self bias. But even though in this case also the stability factor is more only, almost to get proper stabilization, the stability factor should be 1 here. So by using the voltage divider biasing technique, we can able to get the stability factor as 1, so that it can able to provide the required biasing voltage for the common drain amplifier here. So here in the common drain amplifier, if we go with the voltage divider biasing, by utilizing the two resistances R1 as well as R2, we can provide the voltage divider biasing for the FET. So this is RT resistance and this is source resistance. So here we are provide the input signal, and this is the supply voltage VDD here, and here we'll measure the output voltage. So this is the voltage divider biasing circuit for the common drain amplifier in order to achieve proper biasing levels. So once we set the proper biasing levels for the fit circuit, so that we can able to get the proper operating point for the amplifier. So once we set the proper operating point, we can get the signal across the amplifier without any clipping or without any variation and without any distortion across the output. So to make it the signal is a perfect amplified signal, we have to provide the proper biasing here as well as stabilization. And we have to take the necessary conditions to provide the stabilization also once we fix the proper operating point so that it can be stabilized here. So while coming to the problem, the first problem, for a common drain amplifier, it is shown in the figure. The transconductance is 2.5 millisiemens and the small RD resistance is 25 kilo ohms. And from this we need to calculate the input impedance, output impedance as well as voltage gain of the common drain amplifier here. So first I am showing the given common drain amplifier here. And this is given in the problem itself. Common drain amplifier with the drain resistance RT. So drain resistance is not given directly. The supply voltage VDD, and through the coupling capacitor the signal is connected to the gate and also having the gate resistance as 1 mega ohm RG and the source resistance is 3.3 kilo ohms. And again by coupling capacitor we are measuring the output voltage V0. So it is C1, C2 here. So in this case we are measuring the output voltage across the drain terminal. So this is the given circuit in the problem. So from this we need to calculate the given values. GM is 2.5 millisiemens. RD resistance when body effect into consideration 25 kilo ohms. From this, how much is the input impedance, how much is the output impedance, and how much is the voltage gain here. So to calculate the input impedance, the first parameter Zi is equal to, for if we observe the circuit here across the input side we have only the single resistance, that is the RG resistance. So the input impedance is directly equal to the RG resistance and that value is given it as 1 mega ohm here. And the next parameter we need to calculate here it is output impedance, that is Z0. So here it is 1 by Gm parallel with the source resistance. Okay, so here the Gm value is given it as 25 into 10 power minus 3, sorry, 2.5 into 10 power minus 3, and this will be parallel with the source resistance 3.3 kilo ohms. So we can write it as, so this value we will get approximately 400. So 400 into 3.3 kilo ohms divided by 400 plus 3.3 kilo ohms. So after simplification we will get it as 356.76 ohms as the output impedance for the given common drain amplifier. And next we need to calculate the voltage gain. Voltage gain AB. So the formula for this is the transconductance Gm into the parallel combination of body resistance as well as source resistance divided by 1 plus Gm of RD parallel with RS here. So the values of it one, two GM value is 2.5 into 10 power minus 3, and the RD value is 25 kilo ohms, and it is parallel with again source resistance 3.3 kilo ohm. So 1 plus again GM is 2.5 into 10 power minus 3 into 25 into 10 power 3 parallel with 3.3 into 10 power 3. So if we simplify, we will get the voltage gain value as 0.899. So this is the voltage gain of the given common drain amplifier. Yes. While coming to the next problem, this is also a common drain amplifier. It is shown in the figure. Has the following components. Here they given it as R1 as well as R2 resistances, means this common drain amplifier is biased with the voltage divider biased, and the source resistance is 4.5 kilo ohms and the load resistance is 35 kilo ohms, and the FET parameters, that is transconductance, is 5000 microsiemens, and the small RD value is 64 kilo ohms. From this, we need to calculate the input impedance, output impedance, as well as voltage. Okay. So, before going to solve the problem, first of all, I'll get the given circuit in the problem. So, in the given circuit, we're having the R1, R2 resistances for the gate terminal of the transistor, and also the source resistance RS is given, and through the coupling capacitor C1 input signal Vs is applied. So here we are giving the plus VDD supply, and again the output we are taking across the source. Why? Because it is common drain amplifier. This is CC here. So the input impedance this side and the output impedance from this side we need to calculate, and here we are also having the source voltage Vs across the source terminal and the gate voltage Vg across the gate terminal. This is the gate, drain and source terminals. So this circuit given here, and along with this circuit they given it as the R1 value as 2.5 mega ohms and the R2 value is 750 kilo ohms, and the source resistance value is 4.5 kilo ohms, and the load resistance value is 35 kilo ohms, and GM, the transconductance, is 5000 millisiemens, and RD is 64 kilo ohms. These are the given parameters. So from this, we need to calculate the input resistance and the output resistance as well as voltage gain of the given common drain amplifier. So further, to calculate the first parameter, that is input impedance, ZI. So in the case of this circuit, for the gate terminal or across the input side of the circuit, we are having two resistances, R1 as well as R2. So the input impedance is the parallel combination of R1 and R2 here. So we can write it as R1 into R2 by R1 plus R2. So the value of R1 is 2.5 mega ohms. It is 10 power 6 into, and the R2 value is 750 kilo ohms divided by 2.5 into 10 power 6 plus 750 into 10 power 3 here. So here after simplification, this value we will get it as 576,923.07 ohms. So this is the input impedance for the given common drain amplifier. And the second parameter we need to calculate here, it is output impedance. That is Z0. Output impedance Z0 is, know that 1 by Gm parallel with source resistance here. So the Gm value given it as 5000 millisiemens. It should be parallel with 4.5 kilo ohms. That is source resistance value here. So this value we will get it as 0.0002 into 10 power 3 into 4.5 into 10 power 3 divided by 0.0002 into 10 power 3 plus 4.5 into 10 power 3 here. So after simplification it is 191.48 ohms. Z0 values. And the next parameter is the voltage gain. Voltage gain AV. So that is Gm into Rd parallel with Rs by 1 plus Gm into Rd parallel with Rs value here. So Gm value is 5000 into 10 power minus 3 and the small Rd value is 64 kilo ohms. It is parallel with 4.5 into 10 power 3 divided by 1 plus 5000 into 10 power minus 3, 64 into 10 power 3 parallel with 4.5 into 10 power 3. So if we expand this expression for the simplification, we will get it as 5000 into 10 power minus 3 into 64 into 10 power 3 into 4.5 into 10 power 3 divided by 64 into 10 power 3 plus 4.5 into 10 power 3 whole divided by 1 plus 5000 into 10 power minus 3 of 64 into 10 power 3 into 4.5 into 10 power 3 divided by again 64 into 10 power 3 plus 4.5 into 10 power 3. So after simplification of this one, we will get it as 0.999 as the voltage gain of the given common drain amplifier. So while coming to the next problem, it is a common drain amplifier shown in the figure. I'll show the figure now. Has the following components: R1 equal to 2.7 mega ohms and R2 resistance value is 830 kilo ohms and the source resistance value is 4.7 kilo ohms and the load resistance value is 33 kilo ohms and the fit parameters Gm equal to 6000 microsiemens and Rd resistance is 70 kilo ohms. So from this we need to calculate the input impedance and the output impedance as well as the voltage gain here. So the circuit given in the problem is, so once R1, R2 is given in the problem means again it is with the voltage divider biasing for the common drain amplifier. So it is VDD. Here we apply the source voltage. This is R1, R2, C. And here we measure the output voltage V2. And here we are having the gate voltage. And here we are having the source voltage This is source resistance. So R1 is 2.7 mega ohms, R2 is 830 kilo ohms, and RS is 4.7 kilo ohms. This is the coupling capacitor to couple the output voltage or to measure the output voltage. And we are also having the load resistance RL. So this is the circuit given. So from this circuit we need to calculate all these input output impedances as well as the voltage gain here. So for that purpose, I'm going with the input impedance calculation first. Input impedance ZI is, so here again we are having two resistances in the input section of the circuit. So we need to take the parallel combination of the two resistances R1 and R2. That is R1 into R2 by R1 plus R2. So R1 value is 2.7 mega ohms and R2 is 830 kilo ohms. And again it is 2.7 into 10 power 6 plus 830 into 10 power 3. So if we simplify this, we will get it as 628977 ohms input impedance. If we observe in the common drain amplifier, we are getting very high input impedance. Why? Because in the ideal case, input impedance must be infinity. So that's why in the practical case also we are getting high input impedance. And the second parameter we are going to calculate here, it is output impedance Z0. It is equal to 1 by transconductance parallel with the source resistance. And the transconductance value is 6000 micro Siemens. This should be parallel with 4.7 kilo ohms. So this value we will get it as 166.67 parallel with 4.7 kilo ohms. So if we write it as 166.67 into 4.7 into 10 power 3 divided by 166.67 plus 4.7 into 10 power 3. So if we simplify it, we will get it as 161 ohms as the output impedance. And next parameter we need to calculate here, it is voltage gain. Voltage gain A. So to calculate the voltage gain, we are having the formula GM into parallel combination of RD resistance, RS resistance. Here we are also having the load resistance in the given circuit. So that's why we have to add that load resistance also into consideration. Divided by 1 plus GM of RD parallel with RS parallel with RL here. So the GM value here, it is 6000 into 10 power minus 6, and the small RD value is 70 kilo ohms. Source resistance is 4.7 kilo ohms, and the load resistance is 33 kilo ohms. Divided by 1 plus 6000 into 10 power minus 6 into 70 into 10 power 3 parallel with 4.7 to 10 power 3 parallel with 33 into 10 power 3. So this value 6000 into 10 power minus 6. The parallel combination of all three resistances, if we calculate, we will get it as 3885.7 divided by 1 plus 6000 into 10 power minus 6 into 3885.7. So after simplification, we will get it as 0.959 as the voltage gain of the given common drain amplifier. So in this way, in the case of a common drain amplifier from the given common drain circuit, we need to calculate all the amplifier parameters like input impedance, output impedance, as well as voltage gain here. So here the depends upon the given circuit. We may get either fixed bias circuit or voltage divider bias circuit or self bias circuit. So depending upon that, some resistance values will be varying here, but the formulas are same in all the three biasing circuits.
Like, share and subscribe. Hit the bell icon for more updates.